Welcome back. In the previous video, we dwelled upon posterior probability and derived the equations for sigma, that is sigma h, and the mean of the posterior. Now we'll continue to build on these concepts and derive the equations for Kalman filter from here. So once again, I have written down the sigma h equation here, and here what I've done is that I have defined a variable called k, which is generally known as Kalman Gain. And this has been defined in the following manner: sigma 1 square divided by sigma 1 square plus sigma 2 square. So let's say this is the variable. Something very interesting happens if I do 1 minus k, and what I get after doing 1 minus k is that these terms will cancel out, that is sigma 1 square term will cancel out, and sigma 2 will come on the numerator. So this is what is 1 minus k, and as I told earlier, this is called as Kalman Gain. So once again, I have written sigma h here, and I've just written sigma 1 square, and then the remaining part has been clubbed under this bracket. And as you see, this whole expression is nothing but 1 minus k. So I can then rewrite sigma h as 1 minus k multiplied by sigma 1 square. Note this k is a gain. So 1 minus k is also a gain which is being multiplied to the sigma. It is, in Kalman filter terms, it's called as variance update equation. We'll come back to it later. So now we come to mean equation, mean formula, mean of posterior, which has been taken from equation 5 here. And what I've done is I have split the numerator, so and defined this numerator in terms of mu1 and mu2. So once you do that, very beautifully, this equation actually turns into this part is nothing but Kalman Gain, which I had defined here, k, and this part becomes 1 minus k, and that's the reason we did that manipulation earlier. So this whole equation now becomes like this. This is mu of h, that is mu of posterior, which is 1 minus k multiplied by mean of mu1 plus k multiplied by mu2. So let's see, this is something very interesting that is happening. Actually, if you see, if we treat them as weights, say W1 and W2, then W1 plus W2 is nothing but 1 minus k plus k. It will sum to 1. So sum of the weights will be 1. There are two interesting cases that we want to take up now. The first case is, so basically we are updating the mean of the posterior using the likelihood and prior. So this came from likelihood and this came from prior, and then we have defined some gain, and by multiplying the means of these two, we are updating the mean of the posterior. So there are two cases. Let's say my sigma 1 is very large. That means my radar measurement or my likelihood is extremely noisy or corrupt. It is in fact 9 times noisier than sigma 2, which is my prior. So this is prior and this is radar measurement. So let's see what happens here. I plug these numbers back in the Kalman Gain equation, and I cancel out the common terms. So the Kalman Gain in this case, so for sigma 1 square I just write 9 sigma 2 square, and then in the denominator also I replace 9 sigma 2 square in place of sigma 1 square. So what I am left with is a gain which is 0.9. And similarly, I calculate 1 minus k because I have a coefficient here which is 1 minus k, so it becomes 0.1. So essentially what is happening is that my mean 2, that is mu2, which is related to my prior, is getting multiplied by a much larger number in comparison to the mean of the measurement or the likelihood. And that's very apt because my measurement itself is corrupt. It is having very large sigma. So I should weight the mean of measurement. Whatever is my radar telling me, I should weight much lesser than what my initial belief regarding the position of the car is. So that's the reason prior gets multiplied by a larger number and likelihood is with a smaller number. And this situation is explained in this graph, where this green PDF is having very large sigma, so it's completely spread out and it's very flat in comparison to the prior. Prior in this case is this blue GX, which is very peaky, that means which is having very low sigma, and it is centered around somewhere around, the mean is 4. And then the posterior is this red dashed line, which is almost overlapping over this blue PDF, essentially acquiring the entire characteristics of the prior itself. So the mean has not shifted, and the sigma it has assumed of whatever was the prior. That's why it is overlapping with the prior PDF, which means it has given more weightage to the prior, and it has given very less weightage to this radar measurement, which is a very important point, because my radar measurement is not accurate, it's corrupt. Let's take the reverse case, case 2. In this case, my prior, that means my initial estimate of the car position, is corrupt, 9 times more corrupt than my radar measurement, which means my radar is giving me better information than my belief about the position of the car. So once again, I plug in these numbers in the Kalman Gain equation, and sigma 2 is replaced, sigma 2 square is replaced by 9 sigma 1 square because of this relationship. This signifies that radar estimate is better than the initial guess about the car's position, and it results in a gain, Kalman gain of 0.1. Similarly, I calculate 1 minus k, and it results in 0.9. Now the situation flips in comparison to case 1. Earlier, our radar measurement was very corrupt, so we were assigning very less weight to it. Now the reverse has happened. Our initial estimate regarding the prior is poor. The sigma related to this, that is sigma 2, is very, very large, which means I have no faith in the prior, but I have more faith in the radar measurement. It is more accurate. It is telling me a better estimate of the car's position than what my belief was earlier. So I will attach a much bigger weight, 0.9, to radar measurement than to my belief. And this graph depicts the same thing. So here, the mean here is 0. This blue PDF is basically a PDF with a very large sigma, and this is representing my belief regarding the position of the car. And this belief is very, very highly inaccurate, and as a result, my posterior, that is this red dash line, is hugging the radar measurement. It is almost overlapping with the radar measurement and trusting it more than trusting the belief. So as you see that in this case, my radar measurement is centered at mu, which is 0. So I'm believing that I'm moving in this direction, and I am trusting the radar measurement more in this case. So the posterior is almost hugging the radar measurement, the reverse. And that's how Kalman Gain works actually. It is doing a balancing act between the likelihood and the prior. The likelihood here has come from the radar measurement, and the prior is our initial guess about the position of the car, as explained in the previous video. So as you can see, I'm not very sure if you've ever seen Kalman filter equations. This is how they look. This is Kalman Gain. This one, this is state update, and this is variance update. Look how familiar they are. This is a variance plus this is standard deviation plus standard deviation. So this is very similar to what we are doing here, which is this. This is standard deviation of likelihood. This is standard deviation of likelihood, and this is standard deviation of variance of prior. Similarly, if you see variance update equation, this one, this is very similar to what we are doing here, multiplying by 1 minus k, and this is exactly happening here. And lastly, if you see the state update equation, so here I have gone ahead and opened these brackets and clubbed the k terms together. This is the equation here. So what happens is that I draw out this common k term, so it becomes mu2 minus mu1 multiplied by k. K is nothing but gain, and this is the previous estimate. So essentially, this part is nothing but error between the radar measurement and the initial estimate in the position. This error is getting multiplied by a gain, and then the previous position of the car is getting updated. So if you see, it is quite similar. We have 2 gains here, and the sum of gains is equal to 1. So you can clearly see that Kalman filter equations are emerging from whatever that we've been doing so far, which is Bayesian analysis. I'll see you in the next video.